Before we get going on looking at the shapes themselves, I do want to explain what VSEPR theory is. And we say VSEPR as chemists. It really isn't even close to being VSEPR. It's more like, I don't know. Valence shell electron pair repulsion theory. And it's a very straightforward theory, and I often have other teachers ask me, how do you get them to, well, I guess VSEPR isn't that difficult, but how do I go through hybridization, I go through pi bonds, I go through it in great detail. Some teachers don't. Some teachers will go straight from the Lewis diagram and then go straight into VSEPR theory, and it can be done. You can easily determine the shape of a molecule without knowing anything about hybridization, without knowing anything about pi bonding, double bonds or triple bonds, as long as you simply follow a set of rules when it comes to looking at the Lewis diagram and just following those rules and getting a shape. It can easily be done. I'm a firm believer that if I explain in more detail the hybridization and where it comes from, then our lesson here today, which is kind of like culminating everything that we've done at this point to get the shape, becomes very easy because you can start to think about what the hybridization is, which means you have the electron pair arrangement, which means to get to the geometric shape becomes an easy last step. Really what I'm teaching you here today is the last step of a procedure that you know how to do because we've done it for a week. So I hope that you guys have a little better understanding than just going from the Lewis structure. But this theory or this particular structure, and I do want you to write this down even though I've been talking about this for a week. But this idea of the VSEPR theory, like I said, you can determine the shape of a molecule just from the Lewis diagram and nothing else. And again, like I said, having no knowledge of any of this other stuff that I've been talking about. You don't have the same understanding, but you can do it. Now, all of this stuff that you're writing here is stuff that I've already been telling you. So as you write this, hopefully it's more of a, oh yeah, he said that, that's good. We'll write that down. And that's exactly what it is. Now, as you are writing that, I'm going to hand out a chart that summarizes all of the shapes that we're going to be looking at. And this is going to help you out in the beginning. But in the end, I'm going to be as so mean as you don't get to use this chart on a test. This is not one of those charts that you get to take in. Some teachers do. I think this is something that you can easily store in your mind. And that's because it follows systematic rules. I've got no problem letting you use something like the periodic table where all those numbers of those mass numbers are things that you can't possibly have memorized. But this type of thing, you can follow some simple logic and get the shapes. So lone pairs are not involved in a chemical bond. Lone pairs are not considered in the overall shape of the molecule. Again, I've explained to you that when chemists use X-ray diffraction, that only massive nuclei are able to be seen. We cannot locate the position of the electrons themselves, so we don't consider them in the shape. Lone pairs occupy a larger region of space and have a small effect on the bond angle. When I say small effect, it means that it does squeeze those bond pairs together a little bit sometimes. Bond pairs are sigma bonds only. We do not consider the pi bonds. The pi bonds, they do kind of affect shape, but in this idea we say they don't. We ignore them completely. Like here in our picture of sp, there's our two sp orbitals, and those unhybridized p orbitals are perpendicular. So we simply say those sp orbitals are repelling away to form that nice linear shape. Bond pairs are a little smaller. They're not as spread out because they're being attracted by two nuclei. There's two sets of positive charges on each side of the pair of electrons, and it kind of attracts them in and reins them in. Again, information that you already know. This lesson, again, was created by a teacher that liked to just go from Lewis diagram straight to VSEPR theory, which is why this is all being kind of redefined here. I think it's good to write this stuff down. I don't think it's useful to write this down. Oh, look at those two are bond pairs, and those two are lone pairs. We're okay with that? Yeah, I thought so. Good. Now don't write this down either. This is those slides that I've had to write down multiple times. I actually have it right here in front of you. At some point in time, if you want to put that summary, you can, but I have that summary right here on this little page that I gave you. It's on the left-hand side, and it tells you, now, you'll notice at the top of that heading on the left-hand side, it says base geometry. I've decided to call that something else over the last couple of years. If you could change base geometry to EPA, that's our electron pair arrangement. In other words, how are the electron pairs oriented? And when we say electron pair arrangement, I'm talking about whether they're bond pairs or lone pairs. All right? And that's where we're at in terms of our describing a shape. If I give you something like sp3d, whether there's bond pairs or lone pairs, I've been wanting you to write down, where's my sp3d2? Did I lose? And oh, it's still on the paper. Oh yeah, there we go. You better bring them out. So if I give you something that's hybridized sp3d2, then the electron pair arrangement is trigonal bipyramidal. And when we talk about electron pair arrangement, I don't distinguish between lone pairs and bond pairs. I'm just counting them all up, right? That's how we determine the hybridization. Lone pairs plus bond pairs. So all of these slides here are just reminding us that if we've got sp, we've got two bonds, the electron pair arrangement is linear. If we've got sp2, we've got three orbitals, and the electron pair arrangement is trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. All right? So I think we know that. Again, we've done this step over and over again. All we have to do now to use VSEPR theory is to ignore the lone pairs and describe the shape of what is produced when we don't take into account the lone pairs. So we've done everything except ignore the lone pairs. So that's all we have to do in order to get what we would call the molecular geometry, which ignores the lone pairs, as opposed to the EPA, which takes everything into account. All right. So, again, we've done this already. Let's not write this down. Draw the Lewis structure. Determine the hybridization, and, again, I'm changing this. I used to call it base shape EPA, the electron pair arrangement. Treat double and triple bonds as single bonds. In other words, ignore the pi bonds. Determine the molecular geometry using the number of lone pairs and bond pairs around the central atom. In other words, we're ignoring that lone pair in order to get the shape. So let's talk about the shapes. Now, Here's where I've kind of deviated on how to present this information. So I think I'm going to just go straight to that page that I've given you, and I'm actually going to go to Smart Notebook, where I've got a little more space, and I can write on this particular sheet. And I would have liked to maybe zoom in, but I don't think I can zoom in on this. I don't think I can zoom in really in any program, so I'll try to write it on here. Okay. If I have a molecule that has 2 bond pairs, 0 lone pairs, or 1 bond pair and 1 lone pair, then I will have 2 as the total, and it is sp hybridized. Okay? You know what? I think I might try this with this particular device today. I don't know if it's going to work. Oh, maybe success. All right. So again, 2, 0, 1, 1, 2, sp hybridized. Base geometry, which I've been calling, and we can change that, which I've been calling EPA, is linear. Okay? Now, if they're both bond pairs, then the molecule itself is linear. If I have a line, and I got 2 atoms here, then I have a linear molecule. That's not surprising. It's linear. For EPA, the molecule itself is linear. Now, if I have a lone pair in there, if I have 1 bond pair, 1 lone pair, still sp, EPA is linear. Now the lone pair we don't imagine is there, but we can draw it in. I could put it right there, dot, dot. You could put it there too if you'd like to help you out. And that's what I was doing with all my magnets. I could put that on here. If I have a lone pair there, oh, see that was fun, lone pair. Then we ignore this. I've got 2 atoms here. It's also linear. That's not surprising. It's still a linear molecule. Whenever you've only got 2 atoms, whenever it's diatomic, it's always linear. The closest point between 2 nuclei is a line. So if you've got something that just has 2 atoms in it, it's linear. Let's just go back for a moment here and take a look at this formula notation. This describes a general formula. Notice here A represents the central atom, X represents a bond pair, so like atom X, and then E represents an electron pair, the electrons. So AX2 is a molecule that consists of a central atom A with 2 X's on the ends. Maybe I should have had the letter A in the middle of my pictures here. That might have been a better representation. Here I've got AXE. That's indicating to me that I've got 1 bond pair for the X, 1 electron pair for the E. We're getting okay with the notation? All right, let's now talk about situations that have then 3 lone pair plus bond pairs. Well, if I've got 3 bond pairs and 0 lone pairs, AX3, it's sp2 hybridized. We know that it's trigonal planar from what we've done in the past, and if there's no lone pairs in it, trigonal planar becomes the molecular shape trigonal planar, because there's nothing to ignore. If we move down to where we now have 2 bond pairs, 1 lone pair, AX2E, trigonal planar, there's my pair of electrons in the X, and we call a molecule like that where I ignore that lone pair, we call it bent. It's not that exciting. It's a bent molecule. So all we're doing today is ignoring the lone pair. If I have 1 bond pair and 2 lone pairs, AX with 2 electron pairs, again trigonal planar, and now I've got 2 lone pairs I'm ignoring, and if you wanted to draw them in, they would be on the 120 degree, all right? And if I were doing that with my little simulation here, I'd have a pair there and a pair there, and again I'd have an atom here, linear. whenever you've got two atoms, no matter whether it's sp or sp2 or sp3, if you've only got two atoms, it's linear. So this is what I'm hoping you can do. I'm hoping it's not totally out of the realm of reality to have you memorize that if you ignore this bond pair up here, that you can describe that as a bent molecule. I'm hoping you can do that. So let's go through now all of the other permutations and combinations. So 4, 4, 0, AX4, tetrahedron, tetrahedron. Their tetrahedron isn't great. I think this is supposed to be coming out in front and that's supposed to be going in behind. 3, 1, tetrahedral. You can imagine that the electron pair takes the top spot. And if you think of the electron pair taking the top spot, we get a tripod without a top, and it's a triangular base pyramid. Okay? Remember our trigonal bipyramid? Two of them stuck together? This isn't a bipyramid. There's only one pyramid there. So it's a trigonal pyramidal, not a trigonal bipyramidal. All right? So there it is right there. Trigonal pyramidal. Or you could put trig pyr, and that would be good enough for me. As long as it doesn't have a bi in there. It's not two of it, it's just one. 2 and 2. Start with the tetrahedron. Now you've got the tetrahedron with two lone pairs, probably maybe one sticking out that way and one going in behind that way. It's hard to see the perspective, but again, you're back to bent. If I have two lone pairs, right, actually I'll put the lone pair there and the lone pair there, right, on those two there, a bent molecule. That's water. Water is two lone pairs, two bond pairs, bent. All right? And again, if you've just got one bond pair and three lone pairs, again, it's diatomic, right? The E's don't count in there. The E's are just the electron pairs. So the formula for that thing would just be AX. And even though it starts as a tetrahedral, it's linear again. When you've only got two, it's linear. Okay? And that's true for all of them. For all of them that has, whatever the hybridization is, if it's only got one bond pair and the rest of them are lone pairs, it's linear. It's just a line between the two nuclei that we can see. So let's move on and take a look at the number 5. Now, up to this point, it doesn't really matter where the lone pairs go, but remember, for trigonal bipyramidal, there are two different types of bond angles. There's our 120 in the equatorial positions, and then the 90 in the polar regions. So here is the only molecule, asterisk, asterisk, one other situation I'm going to tell you later, where you've got to worry about where to put the electrons. And I've already given you the idea. If I have a lone pair and they're bigger than a bond pair, where does that first lone pair going to go? Where does it have the most room? In the equatorial position, right? In that equatorial position. So we start putting the lone pairs in the equator first, and then once we fill that up, we can put a lone pair at one of the poles. And that's what determines the shape. So, taking a look here, trigonal bipyramidal, there it is, trigonal bipyramidal. And then 4 and 1, trigonal bipyramidal, and we call it a seesaw. I don't know if you can see the seesaw, you know what I mean, like a teeter-totter? Yeah, very good, yeah. Callahan's turning her head sideways, and that's exactly what you got to do for this one. See, those are the legs on the seesaw, you see it? And so you can think it goes up and down like this, woo, right? You see it? No? Not buying the seesaw? The lone pair would go right there. Boom, boom. All right? And I guess if you don't have to draw this, if we want to put the seesaw here, we're going to put some kids on the seesaw. Having fun on the seesaw. Yeah, there's one kid there. There's the other kid there, having fun on the seesaw. No? No need? All right. Okay. Again, as you continue to add the lone pairs, they will go in the equator. So one pair over there, one pair out front. And I can show you on here, two lone pairs. Put one on that one, put one on that one, so we're ignoring those. T shape. And add another lone pair, and you are again in the equator. Linear triatomic. I don't really need the triatomic part, but what they're saying is it's linear with 3 atoms in a row, where then your last lone pair, I was going to put an E for an electron. I thought that was going to be fun, but I like these better. You can put a top and a bottom, linear diatomic. Okay? So with sp3d, put them in the equator first, because it gets the most room there. Fill those 3 up, then put one in the top, and then you are, you're done. You've got the molecule. And moving on to 6, 0, octahedral, nothing exciting there. 5, 1, octahedral. Now, with an octahedron, they're all 90 degrees, so it doesn't matter where your electron pair goes. My magnet isn't going to be able to stick because it's not going to go through all that. But it's easier to visualize it if you put it at the bottom, because if you put it at the bottom, you can see now we've got a pyramid that is a square base. So it's a square-based pyramid. Square pyramidal. Again, however you write that is fine. Square pyramid would be fine, right? As long as it makes good sense. Now, at this point, I said, this is the only time you've got to worry about where to put the electrons. The second pair of lone pairs for the sp3d2 has to go in a certain spot. You can see the page to see where it goes. But if the lone pairs are bigger and they're going to push away from each other harder, where's the second pair have to go? Where's the second pair have to go, do you think? Yep, at the top. Because it's going to want to be as far away from the other lone pair because it's bigger. So this is the second situation where you've got to worry about where it goes, and that makes it then just a square planar. It's going to be a flat square molecule, okay? Now, I guess if you did this and this, it would still be square planar. It just simply has to be on the opposite side of the first lone pair. You can't have it 90 and then along the side here doing something crazy like that, because it's going to repel away and the lone pair is going to end up over there anyway. So, octahedral, here let's put some lone pairs in maybe to finish this off. I didn't put the lone pairs at the top, but we'll put some lone pairs in here. There they are on the bottom. There they are on the bottom and the top. And now it doesn't matter where it goes again, top, bottom. This one's kind of in the back here. And again, we're back to a T-shape. T-shape, flat T, because we've taken off one side. And then, oh, look at linear triatomic isn't even in here. I would take this pair away and it would go right across. So again, you could put your dot there if you really wanted to fill that guy in. We could have it go straight across here. And now I've got lone pairs going all the way around this thing. Lone pairs all the way around it on that square plane. And then again, linear diatomic. Okay? So all we've done in today's lesson essentially is to ask you to ignore the lone pairs and then describe the shape, the molecular geometry. Okay? This little AXE notation, it's good to think of, but that's more for those who have not learned anything about hybridization or anything about pi bonding, because they need to latch on to a Lewis diagram that then follows these rules, which then allows them to jump to the shape. The difference between those of you who have learned the hybridization, you can go from here, follow the rules, and just describe the shape, where those who don't know the hybridization have to go from here to a memorized shape. And there's no link towards it. You guys have that link. You should be able to think it through. Okay, let's now just do some examples. On this, oh, and it's too bad that it doesn't show the whole thing. This is also on other sheet. Here's just got a whole bunch of different example molecules that you could have that would follow all these. I didn't hand that one out, but that's not a bad one. If you want to, I'm not even going to worry about the about the website right now, but if you want, right, I don't think those links come through nicely. All you have to do is type into a Google search VSP RE or whatever, ER, I don't know how to do it, VSEPR. Anyway, and you will go to sites that'll have three-dimensional molecules that you can rotate and visualize and all that stuff. Gives you all kinds of examples. We'll show you that table again, but I don't know if that's necessarily functional here at this point. Okay, and I'm going to go through these with you today, and a couple more examples, and then I'll let you work. I'm going to switch over to the, again, Smart Notebook. It works better. So let me just open a file here. File, open. If you haven't written all these down, don't worry about it because I'm going to go over them on Smart Notebook. We're going to go through them the normal way that we've been doing. So you can just put ASICL4 and then we'll do the example. Yeah, I can't write yet. Are we good to go to start the examples here? So we'll just switch over to this. And I hope I can still pick up the black pen. Is it going to let me? SICL4. You know what? You guys know how to do all this stuff. Draw the Lewis structure. Maybe count the valence electrons just to make sure. All right? 4 plus 7 times 4. Because we're not sure whether we're going to have lone pairs on the central atom anymore. So we've got to draw it up. Make sure if we've got that, expanded octet, we've got to make sure we account for it. I do not want to see an orbital view. I do want to go from the Lewis to the 3D Lewis structure, and then ultimately, though, I want the name of that geometry. So what do we got here? 28, 32? 32 electrons? 32 electrons. SI, CL, 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 minus 8, 24? Which means I don't have any extra electrons on the central atom, but we don't know that, right, anymore, so we got to make sure. Which means we can now do our regular analysis, and this leads in directly to our VSEPR theory. 4 bond pairs, 0 lone pairs, 4. Now, if you were memorizing this and learned nothing about hybridization and electron pair arrangement, you would then go to your sheet, and you know what, I know teachers that do that. And they go, oh, there's 4, 0. It's that shape, but that's no fun. It's far more enjoyable if you actually understand what's going on. What's the hybridization? sp3. What's the electron pair arrangement? What did they say? Tetrahedral, tetra. And notice there's no lone pairs, which means you've got nothing to ignore. You can go straight to molecular geometry. What's the molecular geometry? Tetrahedral. And now we can draw a 3D Lewis diagram, which we've been also doing forever. Doesn't matter which direction you put those CLs. Seems a little anticlimactical in that we didn't have any lone pairs to ignore, or nor did we have any lone pairs on the central atom, but still. So like I said, those who just memorize, they need this sheet desperately. But you guys who know the electron pair arrangement and then just have to ignore the electrons, you're far more ahead. Okay? What's the second example? Did anybody get it written down? Or do I have, sorry? What was it? Told us not to. No, that's true. That's good. If you did, I wouldn't have to switch back. PBR3. I would count up the electrons. Phosphorus is in the third row. It could have an expanded valence. You don't know unless you add them up, and that's not true because once you practice enough, you can look at it and say, you can figure out what that picture is once you've done enough of them. But I don't think we've done quite enough. Phosphorus, what is valence electrons? 5? 5 plus 7 times 3, 21, 26. It's a 26er. Oops, I cheated because I know what the answer is. Oh, don't be so stupid. 2, 4, 6, 20 electrons left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh, look I have 2 more I needed on that phosphorus, 19, 20. Now, when you get to the molecular geometry, again, if you've got it memorized, that's great. I'm not letting you have that sheet for the test. But if you don't have it memorized, we are very good at taking that and turning it into a 3D Lewis diagram. Phosphorus, I would put the lone pair there, and then I would put my Br there, and this guy over here, and that guy over there. And then I just have to describe that shape. What is that? Yep. Yeah, trigonal pyramidal. Trig pier is what I would take as full marks. I don't even need to have the whole thing written down. Trig pyramidal. Not a bipyramidal, right? That's something else. So again, as I'm stressing to you, you get to hear, you draw that, you work your way backwards and just describe it using appropriate geometric terminology. And as long as it's explaining it properly, I'm giving you marks. SEBR6. SEBR6. Selenium is in group 16. 6 plus 6 times 7. Well, those are big numbers. 6 times 7. 48. Oh, thanks. I would be heading for the calculator if I was doing the problem myself. SE 1, 2, 3, 4, 5, 6. BR, 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 BR. You know what? If you're paying attention and you realize that I'm not giving you anything that is beyond sp3d2, and the maximum number of bonds you can have there is 6, you could probably jump right to the geometry from here, right? You probably don't even need to add the electrons in. But we'll do it anyway. 2, 4, 6, 8, 10, 12, minus 12, 36. Oh, and we are out. Imagine that. Because I'm not going to, we're not going to have sp3d3. We didn't talk about that in our VSEPR page. We probably could go straight to EPA end to molecular geometry. What's the hybridization going to be for this thing? Yep. Well, yeah, octahedral. Octahedral. And what's the molecular geometry? Octahedral. There's no electrons to ignore on the central atom. And this is sp3d2. And three-dimensionally, we've got up, down, out front, in behind, out front, in behind, all full of bromines. And yes, because it is a Lewis diagram. What was it? I took CO2 away this year because I wanted to cut down on some of the examples because we've seen CO2 multiple times in the past couple of notes. So I just got rid of it. Oh, no, I didn't get rid of it. It says, oh, that's because I restarted. I got rid of it, and then I restarted the program. Let's go straight to CO3. Well, we've done CO2 a whole bunch. Let's just go to CO3. CO3 minus 2? It's got to be minus 2, because that's what carbonate is. Oh, there's 3, 18, 20, 24. Carbon's not very happy, so we should give it a double bond. And this is charged minus 2. So we should put square brackets around it. Now, last day I rushed through resonance structures. I might as well inform you of this while I am doing it. I, during my prep on Friday, made a movie on how to do Lewis diagrams, right? I did all those examples that you guys did except in a formal movie. And then I also did a second movie on resonance structures and radicals. Did you see that there was 2 of them there? And I'm not going to go back and redo that. You can go and watch the movie and get that stuff kind of cleared up, just because I need to get my test in on Wednesday before the Christmas break. So you can go back and look at that. Now, we did quickly look at resonance structures. This is a resonance structure, right? Remember, that double bond could go in those other positions as well. But we're not worried about that when it comes to shape. We don't need to worry about the resonance structures when it comes to shape. When it comes to shape, all we have to do is get a valid structure, and it will get us to shape. How many bond pairs? 3 bond pairs. Remember, we do not include the pi bond. How many lone pairs on that central atom? How many? None. 0 lone pairs. 3. Therefore, what's the hybridization? sp2 and the EPA. EPA. Trig plan, trigonal planar, trig plan, and there's no lone pairs on it, so what's the molecular geometry? Trig plan, not that exciting. Drawing a 3D Lewis diagram. We don't need perspective on this. There is a pi bond that's perpendicular to it, but we don't care about that. Carbon, oxygen, stick a double bond on one of them. Trigonal planar, flat on the board, yep. No, no. If I'm asking for a molecular geometry, that's it. That's fine. If I'm asking for a 3D Lewis, that's it. If I'm asking you a question on resonance, I will say draw all of the contributing structures for this resonance structure. Yeah. So I will ask specifically for all of the contributing structures. And what was that last one? Oh, that was the last one. Excellent. Let me just show you a different type of question. Just put example 2. And don't write all the instructions down. We started to do some of these earlier on when we were introducing you to hybridization, but now I just want to complete it. Our next unit deals with carbon compounds. It's called organic chemistry. And very often we need to know what the geometry is around certain atoms. So the situation is that I give you a skeleton structure. You can draw that. You can put that as A, 2A, because I'm going to give you a couple more of these. Now in this particular example, all of the carbons are happy. We've got all the electrons in there. So all we need to do is kind of analyze the geometry around these carbons. Because in the end, we want to be able to look at the molecular geometry around certain atoms that have other atoms around them. So it's as if we're saying, okay, let's consider the guy on the left the central atom. What's its geometry? Let's consider the guy on the right the central atom. So then we can start to look at geometry of individual atoms. 4 bond pairs, 0 lone pairs, 4 sp3 EPA, that's a horrendous EPA, is tetra, molecular geometry, tetra, and guess what? It's going to be the same for the other one. I don't want to spend a lot of time on this, but what we're essentially asking you to do is look at the geometry around certain atoms that have importance, all right? If they're a terminal atom, and that's the first time I've used this term, in this case hydrogen is a terminal atom because there's nothing connected to it, then I'm not worried about it. But if it's a non-terminal atom, if there's something else connected to it, we need to know what the geometry is around that. Yeah, that's great. Yeah, beautiful. Yeah. So we like to give you the skeleton, and then we say complete the skeleton structure. One way to complete the skeleton structure is to add up all of the valence electrons. Because I might be missing some electrons on this picture. You might already know where to put those electrons, and if you do, that's excellent. But if you're not sure, if you've used up all the electrons, you could still do your 5 times 2 plus 4 times 1. That gets me 14 electrons. I've used 2, 4, 6, 8, 10 to make this thing. So we've used 10. So we've got to put 4 electrons somewhere. Now this is very baby steps. I'm hoping you can just look at that and say, well, of course, nitrogen's missing a couple of electrons. 1, 2, 3, 4. All right? In that case, everything is happy. Again, both of these are identical. So let's just analyze one. Three bond pairs, 1 lone pair, 4 sp3 EPA tetra. We just saw that molecular geometry. What happens when we take one away? Yep. Yeah, trigonal pyramidal. Look at what I just did there. Trig. So I'll use the Y in the trig, and I'll go pier. I'll use the I in the pier this time, just to keep things consistent here. It's good. Excellent. And I'll broadcast that to everyone in the world. Okay, excellent. And let's do one more. Yep, those are our lone pairs. Yep, that's good. That's back when I wanted all those animations. Now, you'll notice all of these are second row atoms, right? Question might be, do I need to add up all those electrons all the time? If there are second row atoms, the ones that used to be must have 8 electrons, but now they're the exceptions, they're the only ones that have to have 8 electrons, then you really don't need to add them up. They're what we called last year nice structures, right? Nice structures, now to you, if you're still using this idea of ugly ones, do I need to add everything up, or nice ones? Nice ones include carbon, nitrogen, oxygen, fluorine, and hydrogen, because everyone is bonding the way it's supposed to. Octet rule, if you added up all the electrons, everything's going to be happy, right? So we could do this without the addition. Anybody see what I need to do to finish that off if I'm not adding up electrons? What do I need to have? Yep.
You need to make a double bond.
Which O would you like? Yeah, double bond for sure. What else do we need? Yep. How many would you like to put there? You don't have to put them in that orientation, but in this case, the way it's drawn, it looks the best that way, yes. Almost there. Yep. Yep, on the other oxygen. So let's do the shape. I'll let you guys work on this for a bit. I want molecular geometry of that guy, this guy, and this guy. Molecular geometry around those things. Actually, you know what? Don't do this guy, because it's terminal. So it really doesn't matter. It's terminal. It's at the end of a run. Even though it has a certain hybridization, we don't care. The terminal atoms are just not the exciting ones in terms of the geometry. And I'll take just the molecular geometry. You guys do all the work. Somebody have a molecular geometry for this first carbon on the left? What do we got? Yep, trigonal planar. It's flat. It'll be 120 degrees. It is trig plan. So if we were to redraw this properly, I would have that O and that H hanging out 120 degrees that way. How about my O here? What is its molecular geometry, Tyson? Yeah, it's bent. It's an sp3 with 2 lone pairs, so it is a tetrahedron where you ignore 2 of the lone pairs, it becomes bent. Bent. And molecular geometry around this one. Yep. Yeah, tetrahedral. It's an sp3, 4 bonds, tetrahedral. Okay. Yeah, that's great. Yeah, it's good. Good stuff. So there is some homework. And I also have an assignment, right? So we're to the point where we're kind of at the end of a big run here.